Hello, so let's start with this Leetcode delete node in a BST. Okay, so we have a binary search tree and we get a root node reference of the BST and the key. We want to delete the node with the given key in the binary search tree and we want to return the root node reference, possibly that we update, possibly updated of the BST. Basically, the deletion can be divided in two stages. We search for the node to remove, and then if the node is found, we delete it. So time complexity should be the height of the tree. And so this is the tree we get a key 3, and we want to find the node with value 3 and delete it. So for example, here we want to find another valid answer is this one. So what we are looking for is, for example, here I want to delete 3. So we want to delete this value 3 and we'll get that result, right? Okay, and another valid answer is that we make, so basically either we make for the root, the parent, or we make to the parent, so one of the two. So there is no like requirement to use one or the other, right? Okay, so we know that we need to find the value. Does it say all of them? Okay, no, we just need to delete one. Maybe there is only one occurrence. And we want to return the root node of the tree, right? Okay, so first we will need to find the node, which shouldn't be complicated. So we should be able to just maybe have some helper here, search which node we are at, and then here we just turn root because we will be modifying the node, right? But we need to call helper on root. Okay, and then we are looking for a specific key. So if we are done, we can just return. We check if node.val is equal to the key. At this point, we should remove this node here. But to remove a node, we need to replace it with something. And we need to reassign its parent to something. So we need a reference to the parent, right? So we need something like here. Starts out with none. And we know we need to look at the left, and the parent becomes the node here. And we know we want to look at the right, and so the parent becomes the node here, and we have right. Okay, now the next step would be to, so when we have this here, we need to pick one of the nodes left to replace it, left or right. Okay, let's just say we will pick always left. One of the problem is that we don't know in which, well, it depends if the node value is smaller or so if node.val is, or maybe just if key is smaller than the parent val, well, that means we are on the left side, right? Else we are on the right side. So what this means here is that the parent that left should become maybe the node that left value, whichever one is not empty, right? So if node that left, then let's just say node that left. Else, let's just give it node that right. And then we will need to change here. We need to make node.right be tied to this node left, this left nodes. So basically we say node is going to be node.left. Okay, actually it's going to be parent.left. Then is it going to be its right value is going to be node.right. Yeah. And same thing here. The right node is, so we are going to put it on the right, which means we don't need to do anything here because the left one is null by count of that. Now here, this means is that it's on the right side, so it's the same thing, except we will wanna to the right, maybe a right, and maybe here, right. There may be some error here, so if it's on the right side, let's just give priority to setting the node.right, and this is going to be left, so, and then I'm going to say right. Then the left is going to be the node left value, and then here, this means, well, we need to say that the parent.right is going to be node.left. And this happens only in the ask case, then we continue looking. Maybe this is one of the solutions, let's see. Okay, so have this edge case here when we have 0, so let's see. So we have a problem in line 14 here, because parent is, so here, what should we do if there is no parent, right? So well, we should just return none at that point, right? Because we're going to remove it. Well, just return actually. Actually, we want to do this at the start here. So if not, well, actually, if root.val is equal to key, then we should just return no. Okay. There is another case when the, yeah, if not root or root.val equal to key. Is there another edge case? Let's see, maybe 1 and the value is 0, or maybe value is 2, maybe 1, 2, the value is 1. Let's see how would those work. Okay, so there's a problem where the second case 1, 2. I should have gotten 2 because I got rid of the parent node. I lost the parent node, so I can't. Yep. What if we had, let's say something where we have like 3, 5, 6, and we wanna remove 5. Okay, intuitively we should have 3, 6. Okay, it didn't remove the node that we want to remove, which is 5. Okay, there's a problem with that. Okay. Okay, seems like this calculation here is very long. Okay, what can we do? So just find where to go in the traversal and don't traverse both. That seems to be one of the things to do here. And then I think passing the plant wasn't too good. Okay, so this is definitely not, using plant here is not the right way to go about doing things. So let's see. Okay, let's do it at the same time. Like, let's now look for the value here, which I'm not taking advantage of the fact that it's a BST here. So let's first just do it like this. So I would look for, let me just keep helper. I like having this helper here. So let's just do node here and keep that. Okay, so if the key is smaller than the current node value, let's not do this here. So this would be like this. And if the node is smaller than the current value, so if the key is smaller than the node value, that means we need to go left. So that means that node left is going to be, we're going to delete from, so this would be helper, or maybe let's just delete helper so that it's a little bit more explicit. And we are going to go left. Okay, otherwise let's go right. But what if it's equal? Okay, now if it's equal, we get here, and that's where we should delete, right? So what we want to do is find pick one of them, right? But let's just say we want to pick the smallest one, right? So let's say, actually, if we want to maintain the binary search tree property, we need to go all the way to the left, right? So so let's get the min of the left side, right? But what if, so basically first if node dot, if there is no node dot left, right? If not node dot left, then we don't have a choice really. So what we can do is just say node, so in our place, because this here means that the key is equal to node dot left. Node dot val. So we have a problem that we don't know the parent. How did they use the fact that we don't know the parent here? Oh, actually, since we are doing node dot left, and here we can just return node dot right, and that way it will be put in there, right? Okay. Now, otherwise, if node dot right, then we could just return node dot left. Turn node dot left. Okay. Okay. Okay, so now that we are here, that means that both are present, so we need to find the leftmost node and make that the parent, right? Because we want all the left to be smaller and all those on the right are bigger, so we can just put all of them on the right, right? So we just find leftmost. Okay. For this node, right? That would be node. Okay, maybe let's just find it here. So while node dot left. So leftmost. Okay. Okay, and then we have that value, so return, we need to so the thing is, it has some values above it, right? So those needs to be on its right because they are bigger. Those along the right ones, right? So now that we find the leftmost, we wanna return it, right? We definitely wanna return that. But before that, we wanna assign its left is not right, but its right needs to be the elements that were on the right of node left, right? but also the elements that were on the left, except the last one. Okay. Actually, we want to still return the root, so we shouldn't do that. Okay, so this is just in case the doing this is weird. Like, why do root that right? Okay, actually, you could do both, I think, right? So you could say thumb equal to this, and then just have val equal to thumb.val, and while thumb that left, just keep doing this, and val equal to the latest val. Okay. And then here just say node dot val, replace it with so you don't need the parent, you can just replace. So that's val, and then node, return node here, dot left is going to be equal to delete helper node dot left for, and that's pretty much it. Okay, so there is a problem with that case. Let me see if what about this case? Like the case where we have 3, 5, 6, and I'm looking for 5. Yeah, it still doesn't delete it, it deletes the wrong thing. So what if I go to the right, do that, try to find it on the right side. Okay, what if we return not the right? Or maybe we should just return this. Interesting. Okay, I think this is confusing, so let's just smaller than sign the left, go left, it's bigger, go right. If the key is bigger, then we probably need to go right definitely. And here this would be if we don't have the left, the right. Since it's not here, should return root. Yeah, sorry. It's to be solved dot the Leetcode and yep, we need to press the key for all of them again. So that will mean so for some reason the value itself Okay, let's debug this. Okay, and let's call it on. So the example that I'm fine with that. Okay, so we want to call it on the, let me just use the tool here, it's tree tool. So dot deserialize, and what we are looking for is the 356 case, and it has a deserialize method, and what we are looking for here is to delete 5. And well, we need to, let me just say here maybe tree tool, draw tree that we get in return, and if we draw that tree, we have just one, which no, maybe that's not running this. Okay, we have 356, so this 5 on the left should not be there. That's the problem. Should have 36. That 5 should be null, and somewhere in our program here we are not doing that. So let's see. So if I go here, and we go like this, that will do run. Okay. Okay, so the node value is, we are looking for 5, we are at value 3, which is the initial, just to confirm here, the initial, so if I say draw tree here, so tree tool, draw tree for this here, just so that you can see, initially, the tree looks like this. Maybe let me comment this so that we can see the initial tree. So the initial tree is that, which is wrong. So, okay, actually this tree here, we should remove 5 and just have 3, 6. So it should be pretty straightforward. Should just remove 5, but we didn't do anything. That's the problem. So let's see. Comment this one out. Okay, so we start out with 3, key is 5, so it's the biggest, so we go to the right. And when we go on the right, now we have 6. So we completely went, okay, so the problem here is actually 356 is not BST. BST, the left side should be 2. So let's say we want 2 here and want to remove 2. What do we get? Does it get removed? It does get removed. So the problem was that it's not a BST on my side, the tree that I gave it. Now, what if we say we want to remove, let's say 3 actually, the root node. So we have a problem because we have 2 duplicated, right? Let's fix that one. Okay, so what happened here is that first we get 3, so 2 is smaller. We should go on the right. 3 is equal, so that's actually what we are looking to remove. So we go here, it's not that. Now we try on the left side, which has try to find the smallest on the left side, so we should end up with 2, right? Because stump here is 2, so the root should be 2. And then the problem is we assign the right side to delete the node on the right, which we have a problem here, right? Because now there's nothing to delete from there. But what if I do left? That's what we want to delete. Okay, so still the same problem. Unless I go on the right and replace it with 6, then I should go and actually remove the root value itself, right? Not yeah. So what I should do is go to the right, and since I placed the far right one, or maybe go on the left, but choose the left side, but delete that from the, so that I can delete 2 here. So now 2 gets deleted, yeah. So this one is correct, but 356, that's not even a correct thing. So 2 and 2 should give me the right solution. Okay, cool. This is the important part, deleting the root value that we replaced it with. I have a small problem here. I'm looking to delete 3, which is the root. What if I go instead on the right and consider basically the definition of equal values to be on the right? I think that's what this means. Okay, so that passes. So another different way this can be solved is, instead of doing the recursion here, we can maybe do something different where we can just assign it right away. So what that would be, and instead of deleting, just assign. So what that will be is, so we need to assign the root value, right? So what we are looking for here is the smallest right node, right? And then to find that, the smallest on the right, we can just keep going left. That's where the smallest elements are. And then root value would be equal to the smallest right node value. And then what we want is to assign to the smallest, to the left side, actually what we want is yep, actually what we want to do is just not assign the value now. what we want to do is, once we find this smallest right node, right, let's just put everything to the left, because everything to the left of the root would be bigger, would be smaller than it, right? Because it's smaller than its parent and it's to the right, so it's bigger than the original parent. So we could just put those to the left of it, and this right node here is already on the right, okay? So with this, we could just return root.right, and this way skipping the root itself that has the value that we want to remove. And now the right side has all of them, because on its smallest it has the left side of the tree, and that's pretty much it. And this is easier to understand, I think. Yeah. So just pick the smallest right node, put all the left side of the root that we want to remove under it on its left, and then on the right, and then just return the right node, right? And that's pretty much it. This should pass. Okay, cool. Okay, so what we did here was go to the far left. Basically, we want to find the node with the smallest value on the right subtree, and then once we find it, we copy its. Actually, let's just go back to the first solution there. So, once we found it here, we copy its value to on the root as on the root, basically the root node, and then we go right and delete this value basically from the right, because if we don't do this step here, well, we have the value duplicated, right? We have it in its initial place, and then we just put it as the root, right? So here, once we put the value in the root, we go ahead and remove it. But what will help us here is that on the next iteration, since we deleted a node that was on the far left, in this case, well, that certainly means that we will get into this case here next time, right? If it's equal to because we will be removing root.val, and we will find that node. And since we went looking for the far left element, that means that it doesn't have any left subtree. Sorry, so that means it will get here actually instead. So it doesn't have any left subtree, and so we'll just return the right node, and then that would mean that we will remove this occurrence that we just put as the root node. I think we could also do it differently, where instead of going for the smallest right node, we could go for the largest left node. That will serve the same purpose, because the largest left node, all the other values on the left side are smaller than it, because by definition it's the largest left node, and all the values to the right of it are to the right of it, or basically that we'll put to the right of it, which were to the right of its parent, are larger than it, because it's smaller than the parent, and those values are bigger than the parent, so by definition they are bigger than this value here. And so to do that, then, well, we are going to look for the largest left node instead, and we are going to start out from the left. And to get the largest left node, that will mean that we will go to the rightmost value on the left subtree. So that would mean we'll keep going right, and then keep reassigning the right value here. So this is the largest left node. And we put that value, which means now we need to delete this value here, which is now root.val, but we want to delete it from on the left side. So we want to go left to delete it, and to delete, we want to replace the left subtree with that, because that's where we will be deleting it. And let's run this and see if this passes. Okay, so it looks like it's accepted. Okay, so that also does work. So there are two ways we can solve this. Basically, we have 4 cases here, right? So the first case is that it's a leaf node, right? The node is a leaf node, that removing it is easy, right? Because we just need to reassign it. The second case is the right subtree is, we have a right subtree but no left subtree, which is this case here. In that case, well, we could just make remove the parent node and just make this right node the parent. Or we don't have a right subtree, but we have a left subtree. Same thing, just remove the parent and replace it with the left subtree. And removing here means just returning the left subtree so that it will get reassigned as the whatever it was here, whatever way we went in order to find the root value. And then, so those are the two cases, like there is no left subtree or there is no right subtree. The third case is we have both. We have a left subtree and the right subtree. And so in that case, we can do two things. We can either get the smallest right node, which is the smallest node on the right subtree, which basically means looking for the leftmost node in the right subtree, and then from there put the value as the root value, and delete that value because we don't want it to be duplicated. So delete it from the right tree, okay? And deleting it is easy because we know we will fall into one of these two cases, because we want to the leftmost of the right subtree, which means by definition that it doesn't have a left subtree, so it means that we'll get into this easy case here. And the other option is to pick the largest left node and assign that as the parent or as the root. And to pick the largest left node, we can just go left and then go all the way and get the rightmost node of the left subtree. And that's what we are doing here with this while loop. And then pick its value and assign that to the root, and then go left and remove the value so that we don't duplicate it. Again, it's the same argument. And then at that point, we assign that as the left subtree after the removal. And then that's pretty much it. So these are the fourth case. We can handle it in two different ways. And here if the key is smaller than the root value, we go left. If it's bigger, we go right. So this is kind of the search part, right? Here we found it because at this point, that means that the key that we are looking for is equal to the root value or the node value that we have here. Yeah, so that's it for coding this problem here. Thanks for watching, and see you on the next video.